I want to present you Kevlin, Henney. We're going to talk about 6 impossible things in development, right?
Yeah.
Let's try that. The stage is yours.
Thank you very much. Okay. Ah, there we go. Right. Good morning. Good morning, Vilnius. Good morning, good afternoon, good evening to anybody watching this later or online now, wherever and whenever you are. So why am I going to talk about 6 impossible things? The 6 impossible things are, let's just get the focus here. This line is taken from Alice, well, actually not Alice in Wonderland, but Through the Looking Glass by Lewis Carroll. And it is in a conversation with the White Queen that the White Queen says, sometimes I believed as many as 6 impossible things before breakfast. Now, I don't know whether you've had breakfast yet, or is breakfast in the future, is breakfast in the past, but we are going to look at 6 things that are impossible. Not 6 things that are hard, or that's a bit tricky, I wonder if we can do that. Well, let's re-estimate that and put more effort in. No, 6 things that are actually impossible, that by definition they are not possible, mathematically or physically. So let's start off with the first one. We're going to do a countdown. Representations can be infinite. Now, this is kind of obviously false. You can't have infinite representations. I mean, we can choose to represent infinity. So you have a representation in a floating point number that says, hi, I'm here to represent infinity. It's not actually infinite, it's just a placeholder. We can also have a negative one. We can also have other numbers that are not finite. Perhaps the most popular of these is nan. Many people around the world have become familiar with nan, thanks to JavaScript. JavaScript has managed to make people increasingly familiar with the fact that computers are not quite as perfect as they seem. And it's presented many people with this profound observation. I love this one from Lufthansa. Tried to parse nan, but it is not a number. Exactly. It isn't. Thank you, Lufthansa, for that deep insight into the IEEE 754 standard. It has got to such a point that now, with many people, whenever they see nan, they assume it's a JavaScript artifact. Now, I think we can blame a lot of things on JavaScript, but the IEEE 754 standard was in the 1980s. Okay, JavaScript was invented in the mid-1990s. We will be talking about time travel later, but that is not a case of JavaScript. What we have here has got to the point where, in many cases, we see some exciting errors. So this was an error from last year. A driverless race car drives straight into a wall. And this was on a racing track, testing driverless cars. And it did 1 lap, and then, after the first lap, went straight into the wall. Why? The initialization lap, something happened, which apparently caused the steering control signal to go to nan, and subsequently the steering locked to the maximum value to the right. When I found this one, I retweeted it, and somebody said, oh my goodness, they're programming cars using JavaScript. Actually, no, it was MATLAB. But people assume JavaScript these days. But I really hope that people actually do start doing crazy things like testing their code. We'll talk about tests later. Because I want you to just remember that driverless cars sometimes have drivers. This would be bad. So the truth about all of this, so I edited a book just over 10 years ago, 97 Things Every Programmer Should Know. And in it, I had a piece from Chuck Allison. And in fact, it's one of the few pieces that I went to somebody with. I actually, I asked people, please submit items. A general call on Twitter. I also approached a number of people. I said, it'd be great if you can contribute something. But Chuck was one of the few people that I approached and said, not only I would like you to submit something, I would like it to be on floating point numbers, and I have a title for you. Floating point numbers aren't real. People assume, because they're taught at school about real numbers, that floating point numbers are real. As Chuck notes, and he's done a lot of work with the floating point standards, real numbers have infinite precision and are therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite and they resemble badly behaved integers. I love this description. You know? So JavaScript is mostly badly behaved. I think we knew that already. But floating point numbers are badly behaved integers. But how well behaved are integers? I mean, if floating point numbers are badly behaved integers, it turns out that regular integers aren't that well behaved either. So I want to take you back in time to 2013. Visual Studio happily informs me that my license will expire in just over 2 billion days. Now, if you're a software developer, you don't just look at that as an arbitrary large number. You recognize that immediately. Your brain goes, oh, that's 2 to the 31 minus 1. Yeah, see, you have a superpower. You think, that's fine, I shouldn't have to worry about it, but apparently I do. Apparently it's going to go stale and must be updated, even though that is long past the end date of probable human civilization. So there's a question here about correctness, getting things right. John Bentley wrote a series of columns for the communications of the ACM in the 1980s called Programming Pearls. And these were collected together in a number of books. And he wrote one, 1983, called Writing Correct Programs. And here he was trying to advocate the use of formal proof techniques for developers. And what he chose to do was to implement a binary search. Okay, not necessarily the hardest thing in the universe, but one of those ones that people often get an off by one error with. Okay, so he said, right, let's do this. We are going to write a correct binary search algorithm. His observations, he sketched it out in pseudocode, and then he added proof-level annotations, basically assertions. And he said, one of the major benefits of program verification is that it gives programmers a language in which they can express that understanding. But he also makes the observation, these techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. Yes, no matter what else, keep it simple, so that if it's wrong, it's more obviously wrong. But one of the other things that he noted in what might be considered an interesting foreshadowing, on the other hand, several professional programmers familiar with these techniques, I don't know who he was hanging out with, but there's not a lot of professional programmers who ever use these techniques. There are only in a couple of companies would people use formal verification in the 1980s. Have related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time, while the bugs are in the easy parts. You've probably had this experience. It's not unique to formal verification. It's called programming. We get it everywhere. You put so much effort into the thing you know is hard, but you kind of completely forget, oh, that's easy. I won't even bother testing it, it's so easy. Where's the bug? It's in the easy bit. So let's fast forward to 2006. This is binary search implemented by Josh Block, who was a student of John Bentley. This is the algorithm, this is the Bentley algorithm in the Java libraries, and it has a bug. That bug was sitting there since 1983 in this algorithm. Why had nobody found it? Because up until the 2000s, people had not really thrown very large arrays at this thing. In other words, they'd thrown kind of big arrays, but 32-bit computing, you were never likely to hit the limits of memory. You were never likely to have an array that was 1 billion or more items in length. The problem is here. It turns out that when you take a very large number and you add it to another very large number, you get a very negative number. You don't get the midpoint. The idea of the binary search is you look for the midpoint between two numbers and you home in on it. Except when those two numbers are really large and you actually have a large array with maybe 1 billion, 2 billion values in it, then you will suddenly end up with something very negative. So this bug can be easily fixed, except for the fact that at school you were taught that these two are equivalent. So this is the whole thing. This stuff doesn't behave like real numbers, doesn't behave like integers. The bug was always there. The bug was sitting there. Integer division, that assumption was sitting there all of that time. So what we learn is that we have assumptions. And I like to think of assumptions as a rather unique piece of knowledge. Assumptions are interesting pieces of knowledge. What is an assumption? It's a piece of knowledge that you have that you don't know that you have. Normally you discover it when somebody contradicts it. We often get this, you know, you look at something, a colleague says, oh, that's not quite right. You say, oh, I had assumed that. In that moment, you have discovered you had an assumption. Before that, you still had the assumption, but you didn't know it. As I say, it's like walking into a dark room, barefoot, and there are Lego bricks on the floor. If you've never had the experience of stepping on a Lego brick in a dark room, you know, I invite you to have children because, yeah, you will discover that. It's a very unique feeling. But this is the point. Even if I told you, in that room there are Lego bricks on the floor, you won't know where they are until you step on them. That is what an assumption is. We'll talk more about assumptions in a bit. So our numbers are not particularly well behaved. This is the USS Yorktown. It's since been decommissioned, but in 1998, they migrated their operating systems from Unix to Windows. They also discovered that they were dead in the water for 48 hours. The source of the problem on the Yorktown was the data contained a 0 where it shouldn't have. When the software attempted to divide by 0, a buffer overrun occurred, crashing the entire network and causing the ship to lose control of its propulsion system. Think of all the billions and billions of dollars spent on military budget can be simply disarmed with the divide by 0. You have the most powerful weapon in the universe. I am presuming, by the way, that that was actually not an artifact of NT, as it was at the time, but actually to do with the fact that it was a driver, because you can't bring down a whole modern operating system just by dividing by 0. If it's running in kernel space and you've written a driver, this buffer overrun, yes, that would cause this problem. But in regular code, that wouldn't do. So what we discover, borrowing from Shakespeare, is about the finiteness of representations. This is the monstrosity in Lovelady that the will is infinite and the execution confined. The desire is boundless and the act a slave to limit. There is this constraint, which kind of takes us into a related area. The fifth impossible thing. Every question has an answer. So let's do a bit of time travel. One of my favorite examples from a few years ago, in fact, probably from the time before Facebook started destroying democracies. They still had bugs. For some reason, I decided there was some bug, and I thought, you know what, I'm going to report that to Facebook. Your feedback will be used to improve Facebook. This statement is false. Thanks for taking the time to make a report. Time. How much time? That's a lot of time. That number seems kind of close to something. I wonder what that number is close to. Well, if you look at the Posix Standard, which is an IEEE standard, second IEEE standard today, it specifies that the time function upon which pretty much most systems, doesn't matter whether we're talking C, JavaScript, whatever, are based, shall return the value of time in seconds since the epoch. When is the epoch? Well, you know, all you have to do is look around, you'll find it. Here's another nice error. There it is. Apparently, Intel had updates back in 1970. The 1st of January, midnight. That is the beginning of time. Which, interestingly enough, means that if you were born before this, which I was, you are a timeless and eternal being, which is kind of cool. And my plan is currently that I hope to live beyond the end of time. 32-bit signed time ends in 2038. So I will technically have lived forever, which is quite cool. It's the only superpower I've got. So that's the beginning of time. So why did we end up on the 31st of December rather than 1969, rather than the 1st of January 1970? Well, this lovely observation from Anil Dash: the natural enemy of the programmer is the time zone. I'm in the UK. Facebook is a bit further west. If you do a time zone adjustment, it takes you, if you've ended up with a 0, it takes you back into 1969, a few hours into 1969. Now, that used to be my favorite theory, but I have another theory I prefer now, which is the real point. If we look at that, you don't have to go all the way into 1969. You don't have to go many hours. If we consult the C standard, it will tell us that the time function will return -1 when the time is not available. You only have to go 1 second back in time to get 23, 59, and 59 seconds. And there you go. In other words, somehow a request for what is the current time was not met. And a value was used. A sentinel value, -1, indicates, I'm sorry, we don't have the time available right now. Now, obviously there's a simple API lesson to be learned here, but that's the key point, is that that idea is that time is not always available. Developers assume that time is a natural thing that is freely available in their code. It's not. It's an external resource. Time and date are external resources. This should also, by the way, inform you why you can't unit test with date and time-based code unless you parameterize them. Date and time are like file handles. They are like database connections. You are not guaranteed they are always available. So let's look at another example of something where a value is not available. Algorithms. People kind of talk about algorithms as being the stuff of computer science. We're going to come back to what we mean by this in a bit. A process or a set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Okay. Normally when people think of algorithms, they think of sorting algorithms. Anybody who did a computer science degree, you're probably sick to death of sorting algorithms. We've already done binary search. But I've recently started on my blog looking at algorithms that are really not safe for work. One of my favorite is permutation sort. Permutation sort has an astonishingly bad performance. The principle of permutation sort is to basically look through the iteration, look through all the permutations. In other words, if I give you a whole group of values, how do we sort it? Well, I'll just go through all the permutations. One of them will be sorted. When I find it, we are done. In fact, if I write this one out in Python, permutation sort looks a bit like this. I want the result to be a list in common with other Python sorting algorithms. And what I'm actually going to do is I'm going to filter based on a function is sorted, which we'll look at in a moment, and permutations. Permutations is a generator, effectively. It generates all of your permutations in sequence. And there's only one of them that will be sorted. So we just need the next one that is sorted. And it will find that. It's terrible performance. It really is very bad. We can define is sorted for ourselves. We can mess about with our definition in Python. It still looks fairly short. Funnily enough, the shortest definition for this function I actually found is in C++. This is pretty much a one-liner. While there is a next permutation, then keep on moving. At the end of all the permutations is the sorted one. When that returns false, the result is sorted. The performance is absolutely shocking. Surely there cannot be anything worse. Oh yeah, there is. I haven't published the next one yet. I'm getting around to it. There's a thing called Bogo Sort. Bogo Sort is roughly the equivalent of not systematically searching the permutations, but randomly searching the permutations. It's basically equivalent to shuffle it. Is it sorted? No. So actually we could write it like this, while it's not sorted. But actually it succeeds too quickly. If it's already sorted, then it immediately returns. We can address this by making sure that never happens. Even if it's already sorted, we will not immediately return. Now, there's an interesting property here. This may never actually return, because permutation sort is guaranteed by systematically searching all the permutations to return. It will get to the one that is sorted. If you randomly do it, you are not guaranteed that. In fact, we can make this truly random. In C++, I can actually, it's got a very comprehensive random number library. I can actually tap into a random device. I can use the entropy available typically in my CPU to make it truly random, not a pseudo-random number generator, but an actual random number generator. There is no guarantee that this will ever produce the right sequence. I mean, I will say, I've never run one of these things and it hasn't converged, but that doesn't prove that it always must converge. A probability of almost zero is not the same as the probability of zero. Now, that also leads us to a rather interesting observation. Is technically, Bogo sort is not an algorithm. There is a formal definition. An algorithm is something that terminates. Something that doesn't terminate is not algorithmic. Now, that's interesting because our whole point is that everything has an answer. And we're saying, actually, no, it doesn't. So, how do we test this? This observation from Edgar Dijkstra, program testing can be used to show the presence of bugs but never show their absence. Well, if I want to do a simple test, let's just test it on the Python version. If I test it against 6 digits, then I will say that this does actually, every time I've ever run it, converge. But how could I test that it always works? Basically, I can set a timeout. And what I can do is I can say, when the alarm expires, time out and fail the test. When do we fail the test? We fail the test at the end of time. In other words, if we reach infinity and we have not finished the algorithm, then we fail. You might notice there's a slight problem with this. So normally I choose something more pragmatic, like 1 second. Whenever I run this, it works for 6. I think it fails at around 8. That's how inefficient this algorithm is. It takes longer than 1 second to randomly sort this stuff. So please don't walk away from this talk thinking I must use Bogo sort or permutation sort in my code next week. But there is an interesting point here. What we've actually done is we have solved the halting problem. The halting problem is a computer science kind of observation, actually dates back to the 1930s. Is it possible to determine whether or not an arbitrary computation will terminate, or whether it will never halt, never stop? It turns out we can solve this problem. I mean, it's been proven that you can't solve it, but we're actually going to solve it. How do we fix it? We added a timeout. That's why we add timeouts to things. We say, we add non-determinism. We say, well, either this goes on forever, or it gives us a result. We can't have that. We don't know how to determine that. Tell you what, let's add a timeout, which basically means either we get a result or we get a timeout. That's why we have timeouts. So timeouts are how we solve the halting problem. That's going to be important when we look at a couple of other impossibilities. Every truth can be established where it applies. Now, this is an interesting one, because again, we're really digging into the philosophy of stuff here. And this was an interesting one, because at the beginning of the 20th century, there was this optimism, this huge optimism, that everything was going to be within our reach. We would understand everything, that mathematics would be shown to be complete and consistent, and everything that could be proved could be proved. At the beginning of the 20th century, Physics looked like it was going to give us the answer to everything, that everything could be known and be certain. This story did not end well. Quantum mechanics came along and said, that thing you said about knowing stuff, that doesn't work. And although there was a proof, in 1911, Alfred North Whitehead and Bertrand Russell proved that you had this solid mathematical foundation, Principia Mathematica. Maths was consistent and complete. Everything could be proved. It was true. Kurt Gödel messed this one up in the same way that quantum mechanics messed up our understanding of physics. His incompleteness theorems basically said any consistent axiomatic system, which a programming system is, there will always be theorems that cannot be proven within that system. In other words, there are things that are true, but you cannot show within that system that they are true. The only way to show that they are true is to step outside the system. And once you've created a new system around your system, then you need to step outside that one to show that the truths are all true in that one. Now, normally people think, that doesn't really affect me. I'm an application developer. Why does this make a difference to me? Let's have a look. So this is a kind of a profound insight. Gödel, Escher, Bach was a book based on this and a number of other insights by Douglas Hofstadter. It's kind of a classic book. It was published in 1979. I've ended up with two copies. The copy that is falling apart, that I got in the 1980s, and the copy that I now read that is not falling apart. And he talked about this one. All consistent axiomatic formulations of number theory include undecidable propositions. I'm afraid that's all of programming. How do we determine, do we have any examples? Well, for this one, there are a number of examples, but I'm actually going to revert to an example in C, partly because it's easier to show, because C, I was rude about JavaScript earlier, let's be rude about C. How long is a piece of string? So in C, if you've not done C before, C has a very simple idea of what a string is. It's a sequence of characters, and there is a null at the end. Okay, it's null terminated string. You point to the beginning of the sequence, and you look for the null. Strlen is the function, because by the way, in the 1970s, there was a huge vowel shortage. Okay, we couldn't have long names. So Strlen is as good as you got, one vowel. These days, we have nice long names. But back in the great vowel shortage of the 1970s, you had Strlen. How was this function written? Well, I'm going to borrow from Koenig and Ritchie's C programming language. Let's look at their definition of this. What we have, size t is an integer type representing a size. We start off with 0. Then we have a loop. We are going to loop for as long as the offset from the beginning of our sequence, the beginning of our array. As long as that is not equal to the null character, we will keep incrementing our count. And therefore, when we reach the null character, we have achieved the length, and we return it. Cool. What must be true for this function to work? Well, the first thing that must be true is that that pointer must point to something. It cannot be null. And I can actually prove that. I can write that in the system of standard C, in the system of Strlen. It is possible to prove that actually, or rather, this must not be null. That's easy. But there's also another point, and I put this in grey with some English words and some upside down A's and back to front E's. Because there's also another thing that must be true. What is the thing that must be true? There must be a null. Basically, we're saying, from here, there must be a null somewhere in the future, and it must be reachable, and everything must be defined. Well, how do you prove that? How do you assert that? You can't. You can only prove it by looking at the system outside Strlen and going, this is correct, or this is not correct. You cannot prove inside Strlen whether or not Strlen will execute correctly. But if you inspect the code around it, you can always do that. So for example, if I take a well-defined string and I print it out, be excellent to each other, how long is that string? It's 26 characters. I will get the right answer using Strlen. If I do something that is a little less obvious. Insufficient space. I have said that there are 5 characters here. I have not put a null on the end. In fact, I can write it like this. I have not put a null on the end, but I have told the compiler there are only 5. Please do not put a null on the end. Will there be a null? Well, maybe it runs. Or maybe it doesn't, and you find yourself somewhere beyond definition. For those who are interested, that is M87. At the heart of M87 is one of the largest black holes we know of. That's what happens when you do stuff in C. This one's a great one. For those of you who've never experienced a language that doesn't check that you initialize your variables and doesn't initialize them for you, C can be quite exciting. If you find development boring, I invite you to try C. It'll never be boring again. Here I have an uninitialized pointer. Where is S pointer pointing to? It's not defined. And this is not like JavaScript undefined, which is defined because it tells you my value is undefined. That's a definition. This really is undefined. We don't know where it points. And if you try and do any operations on this, this is what that black hole looks like at the heart of M87. Yeah, that's the experience you have programming in C. Why would you not want this excitement for yourself? So, does this have any other practical implications? Can you find it elsewhere in programming? Yeah, you can find it in every single language. It's just C. It's really easy to demonstrate. But it's also another observation Adrian Collier made in a piece on talking about evaluating the fairness of machine learning systems. As he says, one premise of many models of fairness in machine learning is you can measure or prove fairness of a machine learning model from within the system, i.e. from properties of the model itself and perhaps the data it is trained on. What we know and have known since 1931, so for the last 90 years, is you can't do this. You can't do that. You cannot demonstrate the fairness of a system from within the model that you use to create that system. You have to step outside that to evaluate fairness. This also has other implications. So a rather interesting little experiment in performance art last year took place. Pandemic, people got very creative. Simon Weckert, an artist in Berlin, bought 99 second-hand Android phones. And he turned them all on, and he walked the streets of Berlin. What he did was generate traffic jams. This is how Google Maps works. Google Maps says, well, does Google Maps show you where the traffic jams are? No, it doesn't. It shows you where the Android phones are. Notice that's a really subtle distinction. If you've got 99 Android phones at walking speed down a street, that's heavy, slow traffic. And therefore, he rerouted the traffic around this road, which came up as red. This is a really important observation. Why? Because it affects the whole of the internet. Because people keep talking about this fictitious value called engagement. If anybody ever stands up and says, we increased our engagement, no. Where's your evidence? How do you know you increased your engagement? Well, we've got the click numbers. No. Engagement has a very clear definition. Engagement, the state of being engaged. Can you tell that your user is engaged? Does your web page actually check that the user is emotionally involved and committed to your website? I mean, if your website's really badly designed, they will be emotionally involved, just not the way you want them to be. If you make your website frustrating, you can genuinely say, we increased the engagement. The number of people who never come back to our site is huge. The number of complaints we receive is huge. Yeah, they're engaged. But most people don't measure engagement. They measure phones, wandering streets. They measure engagement. They measure clicks and shares. You are not measuring engagement. Please do not use the word engagement when you mean we've got a bunch of data on how... No, I'm going to even change what I was going to say. I was going to say how people click and share. You don't. You have a bunch of data about events on your web page. You have no idea whether those events originated with a human being. What you have is a lot of data about clicks. This changes the complete economic model of the web when you realize the web does not have an economic model. It's based on a fiction. We must be careful not to confuse data with the abstractions we use to analyze truth. We cannot establish the truth of everything that we need in the place where we need it. Which leads us kind of nicely to 3 and some other realms of philosophy and physics. This one seems really obvious. I mean, it's obvious that you can't know the future before it happens. Yeah, it's obvious when you put it like that. But do we do anything in software that suggests otherwise? Well, actually, we do quite a lot. So Grace Hopper, basically one of the people who invented the concept of the compiler back in the 1950s, she had this lovely observation about what it is that software development is. She said, to me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. What she is saying is, in essence, software development is applied philosophy. By the way, if you're looking for a new job title, if you get to choose your own job title, applied philosopher is quite a good one, okay? It also sounds a lot better at, at parties and Christmas events. Oh, so what do you do for a living? I'm an applied philosopher. Or maybe I'm a cyber philosopher. Maybe I'm a crypto philosopher. You see, there's a lot of possibilities here that sound a lot better than I develop web apps. So let's understand the nature of knowledge. There are things that we know that we know. There are things that we know that we don't know. Okay? I know I can speak English. I know I can program in C. I know I can program in Python. I know I can't speak Lithuanian. I'm very sure of that. There is no surprise to me that I can't speak that. And then there's the unknown unknowns. This is where our assumptions live. I didn't know that I didn't know that. And then, the unknowable unknowns. There is no way for you to find out that you don't know something until the moment that you know it and that it makes a difference. This is where the future lives. It is not knowable until it arrives. Sure, I can estimate things, but I can't know it. Now, why does this matter? This is the most interesting category here. The halting problem. For an arbitrary algorithm, you can't tell whether or not it terminates until it doesn't terminate, for which you have to wait till the end of time. That's quite a long wait. There are other examples. And a reminder here, there's this lovely quote, prediction is very difficult, especially about the future. What I love about this quote is it demonstrates how hard knowledge is. We don't actually know who said it. This is knowledge about the past, and we're not sure. Some people think it's Niels Bohr. I quite like that theory. There's a number of other people that get attributed with this. But what is interesting here is this is knowledge about the past. We don't even know who said this. How on earth can we predict the future? And why would we want to predict the future? Well, because people do ask things like estimates. So this is a rather nice little one that I picked up from Work Chronicles. What's the estimate? A month. What if we add one more engineer? 2 months. If we add a project manager? Trust me, you don't want to know. Feel free to Google this one and present it to your colleagues at some point. Now, this is all good, and you're expecting me to throw some crazy piece of computer science or code at you. No, I'm going to throw at you something completely different. I'm going to move into the product space. I'm going to talk about roadmaps. Many organizations have product roadmaps, architecture roadmaps, team roadmaps. You can go on to Google. I did this last year. Product roadmap templates. Oh my goodness, there are so many templates. And lots of them have roads, just to make sure that you understand the metaphor. You know, to make your life a little more exciting. Make those PowerPoint presentations that little bit more exciting. Your life is filled with excitement now, because now you're going to program in C and you're going to use templates for PowerPoint. And you're going to present your roadmap as this single definite road into the future. There is one small problem with the roadmap metaphor. Let me show you where I live. I live in Bristol. That's a roadmap. Notice it has more than one road. Roadmaps with only one road are pointless. Why would you have a roadmap with only one road? Yeah, it's just like, well, it's down the road. Oh, could you give me a map for that? No, you just drive 5 minutes. What could you give me? No, there's only one road. It's that one there. Yeah, but what if I get lost? Really? We have maps because we need to navigate, because there are choices, because the future is uncertain. A product roadmap that only has one road is pointless. You need multiple roads. And that, you see, the product roadmap metaphor is a good one if we used it properly. Here is what we think might happen in 6 months, 12 months, 18 months. Let me show you one of the other roadmap templates that I found last year. This one, here's an example so you know how to use a roadmap template. What I want to highlight here is 2020. How many people had global pandemic in their roadmap? Global pandemic completely disrupts our markets, our workplaces. Oh yeah, we had that. No, you didn't, because you can't predict the future. That was unknowable until it arrived. So, you know, there's an issue here. There's another issue as well. The standard language of a lot of modern agile development includes this idea. There are lots of people who talk about, oh yeah, we're going to prioritize our backlog. How are you going to prioritize it? By business value. You can't prioritize by business value. I'm not saying you shouldn't. Sometimes people misunderstand me when I say this, so I want to be absolutely clear. I'm not making a recommendation that you shouldn't prioritize by business value. I am telling you what the laws of physics tell us. You can't prioritize by business value because you do not know the business value until some point in the future. I mean, I'll leave aside the fact that the term business value is itself not well defined, but we can define it. We can define it as revenue for us or for our customer. We can define it as a set of benefits. But when do we get the value? Is it in 3 months' time, 6 months' time, 12 months' time? These are all different time horizons. What is the business value of this feature will be this many euros in 12 months' time. If you can say that kind of stuff, it means you have a time machine. And if you have a time machine, why are you standing here or sitting here watching me? There are dinosaurs to visit. What does the future hold? Because you cannot travel in time, you cannot prioritize by business value. Or rather, you cannot travel backward in time. I mean, we do travel in time at 1 second per second, roughly. The sad thing is I can't go back to myself and say, yes, don't do that. In other words, you can prioritize by estimated business value. I had one person tell me, oh, but Kevlin, you're just playing with words. No, I'm not. I'm playing with physics. There's a big difference. If you confuse estimates and actuals, we have a real conversation to have. Estimates are not actuals. So therefore, you can prioritize by estimated business value. And then what you should do is find out what the actual business value was. Just like you do with all other estimates. I'm sure you do that. So, as an observation, again from Grace Hopper, because I'm asking you to change something about the way that you do things. And Grace Hopper says, humans are allergic to change. They love to say, we've always done it this way. I try to change that. It's why I have a clock on my wall that runs counterclockwise. It's also, Grace Hopper is the reason I have a clock on my wall that runs counterclockwise. Because we live in the age of internet commerce, and I felt engaged enough to go onto Google and say, clocks that run backwards. Yeah, nice. You can buy anything. Confuses the hell out of my kids. So, what else can't we know? We can't know distributed systems. By definition, a distributed system is not knowable. My favorite definition, many people's favorite definition of a distributed system comes from Leslie Lamport. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Many of our systems are now distributed. We find this daily experience. My publisher published 97 Things books that I've edited, had this experience a while back. Fire in California, can't read your ebook in Pennsylvania. This is a common experience. It also confronts us with Brewer's theorem, which is probably better known as the CAP theorem. And it is actually a theorem. It was originally a conjecture, but it was proven in 2002, 2003. CAP theorem is basically CAP, consistency, availability, partition, tolerance. Consistency means that in a distributed system, whenever I request a value of a data item, I will always receive the right value. Wherever I ask, I will get the same value. It will be consistent. But I'm not guaranteed that I will get a response to my request. Availability is that you are guaranteed you will always receive a response to your request. That is not a failure response. But you're not guaranteed that you will get a consistent value. Partition tolerance, partitioning is to do with, you have a network, a router goes down, now you have two networks, okay? It partitions, it breaks. In other words, that your application still keeps on running even when there is network failure. The CAP theorem is basically you can have any two, but you can't have all three. I can have consistent values. I will always either receive the same value, whatever I ask, or a failure status, and that allows me, my application, to continue running in the event of any network failure. Or I can always receive an answer, but I'm not guaranteed that I've got the most up-to-date data value. I'm not guaranteed that every time I send that request, it'll be the right one, but I can continue running. Or the one that people often don't think is that useful, I will always get the latest value. But I fail in the event of partitioning. Actually, this works for single processor apps. It's actually quite useful. The CAP theorem is why you cannot have a truly distributed garbage collection system. Distributed garbage collection is not a possibility. When people talk about, tracing garbage collection is not possible in a distributed system. It's why every system that anybody's ever created for distributed garbage collection has two systems. One is for true tracing garbage collection, and the other is guessing whether or not the network is working and using timeouts, our friend. Okay? They're kind of like patchworks. You can't have true garbage collection at the minute you go outside process. Now, this limits what we can know. It's kind of, the CAP theorem is kind of Heisenberg's uncertainty principle for software architecture. And this brings us to a kind of an interesting observation from Douglas Adams, Hitchhiker's Guide to the Galaxy. There's two characters in that. Say, we demand rigidly defined areas of doubt and uncertainty. They are philosophers. There needs to be some work for us to do. There must be something that we cannot know. And this is a truth that is guaranteed in almost every software system that we build. Now, we also need to be careful, though, that we don't fall into a trap. One of the most common experiences I have that I find frustrating is using most web applications. You undoubtedly have this experience. You go and look at something, maybe it's social media, maybe it's some kind of inbox, and it says, maybe there's a summary at the top, and it says, you have 5 items in your inbox. And then you look at your inbox, and there are 4 items. One of these statements is not true. And sometimes people will tell me, oh, Kevlin, that's because of CAP theorem. No. Oh, that's because of eventual consistency. Nope. You're in the same process. I can see 4 on the same UI as I can see 5. That's not CAP theorem. That's just called not programming it right. Okay? In other words, if you have a UI that gives you 2 different answers simultaneously, That is a fault of the programming in the client. It is, don't blame the distributed system. I had it this morning when I deleted something and it didn't delete from the view. Oh, we're just waiting for it to have deleted from the database. Really? You told me it was successful. This has been successfully deleted. Why didn't you remove it from the view? These things cannot be simultaneously true. Pick one, stick with it. Single source of truth. And the final one, technical debt is quantifiable as financial debt. Now this one's quite important because a lot of people misunderstand what technical debt is and what it means. And it doesn't just have to do with the original definition. But let's dig around. So technical debt is an idea that we often attribute. We talk about legacy systems. We talk about the idea that systems become more disordered with time. The inevitable consequence of human involvement. Things become less well ordered. Meyer Manny Lehman in 1980 made this observation in a classic paper. As an evolving program is continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. Kind of sounds like an entropy kind of measure. And we've struggled to find the right language to describe this. How do we talk about this to other people? Because software is so abstract. Do we call it a mess? Do we call it spaghetti? There's lots of different things that we try and sort of make it sound like. The most popular of these is technical debt. The debt metaphor started being used in the 1990s, but it really took off when Martin Fowler popularized it in the early 2000s. Technical debt is a wonderful metaphor developed by Ward Cunningham that helps us think about this problem. So it's a metaphor. That's the first thing to observe. There is this idea, it says, like a financial debt. The technical debt incurs interest payments, which come in the form of extra effort that we have to do in future development because of the quick and dirty design choice. Now, there's an interesting observation here, is that sometimes people have, first of all, taken technical debt to mean just bad code. That was not originally Ward's vision. Not all debt is necessarily bad. Of course, we have a lot of bad experiences with debt, which is probably why that colors that, our thinking. But also, Martin colored it with the specific use of quick and dirty, which in English, basically, that's not good. In fact, he uses that through the original version of the article. He's updated the article so it now reads differently, but historically, this is the wording that he used. So in other words, it's basically saying, we're going to make bad decisions. Whilst that's true, that's not the idea of technical debt. Sometimes technical debt, not all debt is necessarily bad. Sometimes debt is structured. Sometimes we use debt to get something we could not otherwise get, and we have a structured repayment model. But I'm describing financial debt. It's like this, but it's not the same. Why is this important? Because there are some tools out there that will quantify, or rather, they will pretend to quantify. They will say, your code base has 100,000 euros of technical debt. No, it doesn't. The probability that that figure is correct or meaningful is almost zero. If it is correct, that was a matter of luck, not calculation. Because the most important thing about this statement is it's a metaphor. You're not supposed to actually take it literally and say, oh, I wonder how many euros of debt our code base has. There's a very simple reason you're not supposed to do that, is you can't do that because you don't know. Because you can't quantify it. Now, occasionally I get people saying, oh, no, but we have quantified our technical debt. And as I said, I tweeted this one last year, I found myself cautioning against the category error of treating technical debt metaphor literally and numerically, converting the code quantity into a currency value of a dashboard. If you are doing that, you're no better than people who assume that clicks are equivalent to engagement. In fact, it's probably worse. This is just pseudoscience. You cannot know the currency value of the debt in your code base. It is not something that is knowable. But what is interesting is the reason sometimes people say, oh no, we do know it, is because they make an error of category, as I've described. For many people, they assume this is the cost of repaying the debt. So I've had people tell me, oh, no, we have the technical debt in our code base. We developers, we sat around and we estimated how much time it would take to get rid of the technical debt. And that was a number of hours, and then you multiply hours by how much a developer's time costs. Even assuming you are close, remember it's an estimate, even assuming that you are correct, that's still not the technical debt. Technical debt does not equal the cost of repaying the debt. Technical debt is the cost of owning the debt. That's the whole point of the metaphor. I wrote a blog last year for O'Reilly. That's the message of the technical debt metaphor. It's not simply a measure of the specific work needed to repay the debt. It is the additional time and effort added to the past, the present, and the future work that comes from having the debt in the first place. It's not the cost of repayment. It's all of that cost you had in the past, but importantly, also in the future. We've already had a discussion about the future. You don't know the future. So even if we could get the estimate of the present and the past accurate, we still wouldn't know what is the cost of that debt to us in future. It's a metaphor, it's a tool for thinking. The minute you convert it into a number, you are fooling yourself and everyone else, because it's not possible. So, that leaves us at 0, which actually I managed to roughly achieve finishing on time, which is somewhat unique for me. I don't know if we have 2 minutes for questions, but if we... Huh? We have absolutely 2 minutes for questions. So, in which case, thank you very much. Right, so.
We do actually have 5 or 10 minutes if you want, because we have a coffee break.
Good heavens, I know better than to eat into or drink into too much of your coffee break. So we'll cover a couple of questions. Should we start with online and then take any in the room?
I don't know. Do we have anybody?
Do we have anybody in the room with any questions?
It's pretty early morning.
It is pretty, yeah. I mean, you need the coffee to wake up, to then travel back in time to get yourself to ask me the question. Ah, yeah, I see there's a problem here already. You are questionless.
They might wake up later.
Yeah, that's fine.
That usually happens.
You know where to find me.
Yeah, but we have questions online. Justinas is asking, how do you plan your development features if you cannot trust anything and estimation is hard?
You plan them using a roadmap. But a real roadmap, one with more than one road. What you do is you know, let me. There's an implied question in there. Oh my goodness, we can't know anything. It's all going to be hard. Let's give up now. Let me be more constructive than that. Let me talk about the human experience. Humans are incredibly good at a few things. One of them is working with incomplete knowledge. We do it every single day. You wake up in the morning, you do not yet know what is going to happen that day. Oh, you have an approximate idea. I mean, a number of you who are here had an idea that you were going to come in for the keynote. And you have, well done, you succeeded. There's also a number of you who aren't here that also had that intent and didn't make it. I'm sorry, you didn't make it. You know, maybe you enjoyed the party too much. But there's no guarantee that you were going to be here, but also you didn't know what I was going to say. You kind of knew something about it, but you weren't sure because I only gave you a paragraph. So it turns out that humans are very good at working with incomplete knowledge. We do it every single day. That is part of the human experience. You do not need complete knowledge. We are very capable of working with limited knowledge and therefore finding out more. The problem comes when we fool ourselves into thinking that we have complete knowledge. That's where the problems start. If you go into software development saying, I can know everything now, you will have problems. If you say, we cannot know everything now, but let us put down a set of possibilities based on previous experience and the group intelligence of our team, what are the possible paths into the future that we can already see? How do we know we're on each one? That's the value of estimation. The value of estimation, where you have it, is not estimating just in time, but the scale of a task and the level of our knowledge. How much do we know about this? This is one of those things we never do often enough. Sometimes people say, how long is this going to take you? Is that a week, 2 weeks? I had this with one client where actually the real question was, is this even something we know how to do? No, we don't. So why are we worrying about days or weeks or months? We don't even know if it's feasible. Ah, you know what? That sounds like we should do some kind of spike or prototype to find out. Let's find out what we don't know that helps us then estimate. So in other words, that's how I would plan the development. I would basically say, show me the futures. What do we know? What do we not know? What do I have some confidence in? What do I have low confidence in? What do my colleagues think? Because a single person is only 1 point. You need a little more. And then you get a map or a graph of possibilities. That's how I would tackle that, in kind of the same way I do every morning. But I'm not quite that structured.
Okay, we have a question in the audience, I see, and quite a few online popping up.
Okay. I've obviously said something that people have woken up to. Okay, what did I say?
You said literally wake up and get your coffee.
That's true.
I think that happened. Here we go.
Hello.
Hey.
How do we know that we have technical debt until we started to pay it? And like you said, paying in the past.
Yeah.
And when do we know that we need to pay it fully to stop paying?
Okay,
interest?
So that's a good question. How do we know that we have technical debt? There are many. Let's go back to what the metaphor tells us. So sometimes you know you have a debt because you made a specific decision. Yeah? In other words, I don't know, my wife and I have a structured debt. It's called a mortgage. Okay? We did, that wasn't an accident. It wasn't a surprise. It wasn't like, good heavens, we suddenly have a house and we owe a lot of money. That didn't happen. It was a very deliberate choice. Sometimes you have a debt because you know you have a debt. You took it out. It was deliberate. It was intentional. You got a repayment model. Sometimes you have a debt and you don't know it. In other words, you're accidentally running up a value. I had this many years ago. I can't remember the country, but I discovered it turns out that mobile phone calls were incredibly expensive. Without realizing it, I was running up a huge debt because the data cost was massive. That doesn't mean it isn't a debt, but I didn't know that it was a debt. But there came a point of discovery. And at that point, the debt became real. It's like, oh, I've run up this debt. What does that mean in code? So in code, let's take these two things. One is, we know there's probably a better way of doing this, but we don't yet know enough about how the customer is going to use this code, or this is our first experience with this framework. It's probable that we will want to replace this because we're working with limited knowledge at this point. At this point, we should acknowledge we don't know what we're doing, but we're still doing something to find things out. We may need to come back to this. Maybe note it down, put an architecture decision record in place saying the first time we are using this, we're pretty much copying and pasting from the demo pages, okay? We'll probably want to come back and do something later. This is probable debt. This is not general purpose. This is just copy and pasted from online docs. At other times you discover, oh, you know, every time we go into this piece of code, we spend longer than we thought we would. We lose developers in there. We've lost lots of people in that piece of code. We keep having to employ new people to go in and find them. Okay? That's debt. That was debt you didn't plan, but it's accidental. So in other words, the metaphor is not to give us a number. It's to tell us what is our decision process and what is our discovery process. And when everything's going really well, and you're observing, hey, everything's going really well, and this code feels good. Doesn't it feel good to you? Yeah, it feels great. Then I'm going to say you probably don't have debt in that part of code. Yeah, we're looking for what is the feedback from your experience, the team interacting with the code base. That's what's going to tell you whether or not you have that debt. Okay, the numbers can be interesting, the number of debt points you have, but don't push the numbers too hard. They push back.
Okay, we have time for one more question, basically, because your answers are
not short.
Yeah. Anyone in the audience? Good, because we have many questions online. I will have to choose it randomly.
We talked about random number generation earlier. Yeah, we've got this one covered.
Wow, and they're still popping up. Okay.
So folks online, if you still have questions and they are not answered, You can find me on Twitter. My parents gave me an internet unique name. I'm very easy to find. I mean, look, let's put it this way. If the spammers can find me, I'm sure a group of intelligent software developers are quite able to find me.
Okay, I will just literally ask you the last question that we have. Any suggestions for practically managing knowledge about current state of technical debt, whether it was known from the start or we came to knowing it along the way?
That's a good question. How do we manage this thing which I've said you can't necessarily quantify? You can quantify it, you just need to use the right terms and references for it. So for example, if I want to quantify height, I don't measure it in kilograms. I measure height based on length units, meters, okay? So the point there is that technical debt is something that you can point to and you can quantify. You can say it's here, here, and here. Here is a decision that caused us this. You can identify it within the code. So the first thing is to recognize that it's worth talking about, and the second thing is to note it down. And then to note down whether you still have it. Again, I mentioned architecture decision records. If you're not familiar with those, go and Google them. But these kinds of ideas, make it part of the team's discussion. How do we manage it? Do we have debt here? Is the debt, do we have more debt than we had last week or less debt? You know, these are simple things. We can definitely do more or less that without saying, oh, I wonder if we should measure it in euros. Don't do that. You can still point to it and go, there's a thing here that we can talk about and we can potentially improve. Oh, there's more things here than there were a month ago. That's definitely not good. Yeah, so look at it from that point of view.
Okay, we don't have time for more questions, but I think if people can find you on social media, right? And if also they use the hashtag BuildStuffConf, you will know that they are coming from us. And you can, well, if you have time, answer all their questions. So thank you very much. That was all.